In this video, I'll be going through my notes on Level 3 wave systems. A link to the PDF and a list of corrections are in the video description. Wave motion. A wave is a propagating disturbance. They cause a relocation of energy, but not matter. Water and sound waves are mechanical waves, which require a medium to travel through. Light or electromagnetic waves do not. We can classify waves as either transverse or longitudinal. Transverse waves, such as water and light, oscillate at 90 degrees to their direction of travel. So if our wave is traveling towards the right, we see it oscillating at 90 degrees up and down. Half the height of our wave is our amplitude A, where we have our peaks at the top and our troughs at the bottom, and our wavelength is the distance between one wave cycle. Longitudinal waves, such as sound, oscillate in the direction of travel. So if our wave is once again traveling towards the right, our longitudinal wave is just a series of compressions and expansions, meaning that the particles are oscillating in the direction of travel. Once again, our distance for one wave cycle, or peak to peak, is the wavelength lambda. Period is the amount of seconds per wave, or the time taken for a complete wave cycle. For moving waves, it is the time for a complete wavelength to pass a fixed point. Frequency is the waves per second, or the amount of wave cycles per second. For moving waves, it is the amount of waves passing a fixed point per second. Period and frequency are mathematical reciprocals, meaning that we can write frequency is 1 over period, and period is 1 over frequency. Wave speed. Wave speed can be written as the distance divided by the duration. We can also define wave speed as the time taken or period for a complete wavelength to pass a fixed point, or that the velocity is the wavelength divided by the period. Substituting our period is equal to 1 over frequency, we can also write this. Types of waves. In this course, we will cover the following types of waves. Light waves, which travel at 3 times 10 to the 8 meters per second in a vacuum and are transverse waves. Water waves, which are a traveling disturbance of surface and are once again transverse waves. And sound waves, which travel at roughly 340 meters per second in air, are faster in denser materials, require a medium to compress, and are longitudinal waves. Light. Light is an electromagnetic wave, which means it is made up of fluctuating magnetic and electric fields. How light behaves depends mainly on its wavelength. We categorize light into 7 wavelength-dependent groups. Radio waves such as radar and AM and FM, microwaves used in Wi-Fi, Bluetooth and microwave ovens, infrared used by your TV remote to send signals, visible light, ultraviolet used in sterilization and curing resin, X-rays which are used in imaging and radiotherapy, and gamma rays which are used in PET scanning or positron emission tomography. Light travels at 300 million meters per second, or 3 times 10 to the 8. Unlike sound, it does not require a medium to travel through. Sound. Sound waves are propagating waves of compression and expansion. They require a medium to travel through. Although it is a longitudinal wave, it is often represented as a transverse pressure wave, where we see our longitudinal wave, our areas of high pressure are our peaks, and our areas of low pressure are our troughs. The frequency, aka pitch, is inversely proportional to wavelength. Therefore, as one increases, the other decreases. So if we have a large wavelength, we have a small frequency, and if we have a small wavelength, we have a large frequency. Sound tends to travel faster in denser materials. Phase. Phase is a way of comparing different points in a wave cycle. A complete wave cycle is 360 degrees, or 2 pi. Phase difference on a wave. A and B are a quarter of a wave out of phase, which is 90 degrees. A and C are half a wave out of phase, so 180 degrees. A and D 3/4, so 270. B and D is half, so 180. B and F is 2 full waves, so 720. And C and E is 1 complete wave, or 360. Phase difference between waves. Waves lined up are in phase. Shifting our blue wave by a quarter of a wavelength brings them 90 degrees out of phase. Shifting it by half a wavelength means it is now 180 degrees out of phase. Superposition. When a wave occupies the same position as another wave, their amplitudes add together. So if we have a wave of +1 amplitude and +2 amplitude, the resulting amplitude is going to be +3. And if we had the same situation but with a negative amplitude, we'd end up with a -3 amplitude. When waves combine and form a larger wave, we call this constructive interference, of which these are two examples. If we had a -1 amplitude and then added on a +2 amplitude, -1 + 2 gives us +1. If we had a +1 amplitude and a -1 amplitude, +1 - 1 is 0, giving us complete cancellation. When waves combine and form a smaller wave, or cancel out, we call this destructive interference, which we've seen here. Standing waves. When identical waves traveling in opposite directions overlap, they produce stationary points of constructive and destructive interference. This can happen when we have two separate sources, but this can also occur when a single wave is reflected back on itself. And so if we imagine our resulting amplitude at one moment in time, and then half a wave cycle later, we see our pink nodes of destructive interference, where peaks meet troughs, the waves are meeting 180 degrees out of phase, resulting in complete cancellation, meaning that at these points here, we're going to see no movement. At our blue antinodes, we have constructive interference, where peaks meet peaks and troughs meet troughs, so our waves are meeting in phase, and we get a combined amplitude. And so at our antinodal points, we have our maximum movement. This here is a Tibetan singing bowl, though it goes by many other names. By dragging this leather-wrapped mallet around the outside, we can excite the bowl to create sound. Similar to a wave on a string, the bowl exhibits harmonics. Our first harmonic can be thought of as just a simple squeezing and stretching of the bowl. Here you can see there are 4 regions of the bowl that are moving in and out, corresponding to 4 antinodes. Now, while this motion is too quick and too subtle to notice with the eye, we can notice it with the ear. If you listen closely, every rotation of the wrapped leather will be accompanied by 4 increases in volume, corresponding to our 4 antinodes. What we're essentially doing is dragging this pattern around in a circle. As with a wave on a string, you can also get higher harmonics, such as this one here. String harmonics. When a string is vibrated, multiple standing wave patterns are formed simultaneously atop each other. We call these patterns harmonics, each with a different wavelength and frequency. A string fixed at both ends has nodes at both, which makes sense because as these ends are fixed, they are areas of no movement. And so our simplest pattern of vibration is our first harmonic, which we refer to as our fundamental, where our string is just going up and down. What we have here is half a wavelength, as we can visualize by extending it out, where this distance here is L, meaning that our total wavelength is 2 times L. The frequency of this harmonic is referred to as the fundamental frequency and denoted F0. Our second harmonic, also referred to as the first overtone, introduces an additional node right in the middle. The second harmonic is just an entire wavelength, and so our wavelength is the full length of the string L. You might note that our wavelength has halved from 2L to L, which means that our frequency must have doubled. Our third harmonic, or second overtone, introduces yet another node, and if we divide our pipe into thirds, you might note that our wavelength is 2/3 of this length. Because our wavelength is literally a third of our fundamental, we must have 3 times the frequency. Our fourth harmonic, or third overtone, introduces yet another node, and you might note that our full wavelength is half of our length. Because half of L is a quarter of our original 2L, we must have 4 times the frequency. We'll stop here, but it's important to note that these harmonics do continue forever, albeit at reducing amplitude. The equipment here is set up to generate waves at a frequency shown on the display. The waves then travel down this length of elastic and reflect off the end, interfering with the original waves and producing a standing wave pattern. In this case, at our fundamental frequency of 4 Hz, we see the first harmonic. To get our higher harmonics, we just need to multiply our fundamental frequency of 4 Hz by whichever harmonic we're looking for. So for our second harmonic, that's 8 Hz. Third harmonic is 12 Hz. Fourth harmonic 16. Fifth harmonic 20. Sixth harmonic 24. Seventh harmonic 28. And eighth harmonic 32.
Open pipe harmonics. An open pipe has antinodes at both ends. So once again, our first harmonic is our fundamental, and the simplest pattern possible with antinodes at both ends is this one here, with a node in the middle. And once again, extending this out, you might note that the length of the wave in the pipe is half of our full wavelength. And so a full wavelength is equal to twice our length. And once again, our frequency is the fundamental F0. Our second harmonic, first overtone, contains a full wavelength, and because the wavelength is halved, we have double the frequency. Our third harmonic second overtone, similar to the wave on a string, has a wavelength of 2/3 L and a frequency of 3F0. Our fourth harmonic or third overtone is also the same. And as mentioned, our harmonics can go on forever, but at reducing amplitude. Note that although we are representing these patterns as transverse waves, they are in fact longitudinal. So we're representing them in this way, whereas in reality they're more like this. Closed pipe harmonics. A closed pipe has an antinode at one end and a node at the other. This results in only odd harmonics. And so our first harmonic is the simplest pattern possible, which is this one here, which is a quarter of a wavelength, meaning that the wavelength is 4 times L. And our frequency is once again F0. Because a second harmonic isn't possible, we skip to our third harmonic, which is our first overtone. The next pattern that's possible is this one here, where our wavelength is 4/3 L, and because we've got a third of our fundamental wavelength, we have 3 times the fundamental frequency. For our fifth harmonic, second overtone, our next pattern is this one here, where our wavelength is 4/5 L, and because we've got a fifth of the fundamental wavelength, we have 5 times the fundamental frequency. Lastly, our seventh harmonic, third overtone, has this pattern here. The wavelength is 4/7 L, and because it's a seventh, we have 7 times the frequency, and so on.
This is a Ruben's tube. It consists of a metal pipe, closed at one end and with a speaker on the other. The pipe is filled with flammable gas, which exits through small holes in the top, and is ignited to display a standing wave pattern. The pattern in question is formed when the speaker produces longitudinal waves, which travel down the pipe, reflect off the end, and interfere with the original waves, creating nodes and antinodes. As I play a pure sine wave and increase the frequency, we can observe both that the wavelength decreases and that the pattern is more pronounced for specific frequencies. These frequencies, as should come as no surprise, occur at regular intervals since they are multiples of the fundamental frequency.
Why closed pipes don't form even harmonics. Closed pipes require an antinode at its open end and a node at its closed end. So as you might recall, our first harmonic looks like this, with a node at our closed end and an antinode at the open. Because each additional harmonic is a multiple of this first harmonic, each additional harmonic adds on another quarter wavelength. So for our second harmonic, we start with our first harmonic and then add on another, which gives us a node at the open end, and because we require an antinode at its open end, this second harmonic is impossible. For our third harmonic, we start with our first harmonic, add on another, and we finish off with an antinode at the open end, which is of course possible. For our fourth harmonic, we start with our first, add on another, and then add on another. Finish up with a node at the open end, which, as discussed before, we need an antinode at this open end, and so our fourth harmonic is impossible. For our fifth harmonic, we have our 1, 2, 3, 4, 5 quarter wavelengths, giving us an antinode at the open end, which is of course possible. If we continued on with high harmonics, we would continually see that our even harmonics would be impossible. Timbre. Notes played on musical instruments consist of all the frequencies of the excited harmonics superimposed. The physical structure of an instrument affects how much each of these harmonic frequencies are emphasized. This gives every instrument a unique sound signature, which we call timbre. A tuning fork might give us a clean sine wave, whereas instruments such as guitars, trumpets, and a keyboard might give us something a bit more hairy. Beating. When waves are observed from two sources at different frequencies, the waves alternate between in-phase and out-of-phase. This results in moments of high amplitude constructive interference and low amplitude destructive interference. We call these beats. The frequency of these beats is the difference between the two constituent frequencies, and so our beat frequency is the magnitude of our two constituent frequencies. These two lines just make whatever's inside positive. Here we have two speakers playing separate frequencies, a microphone in the middle, plugged into an oscilloscope at the back. Currently one of the frequencies is much higher than the other, but as we drop it down, bringing the frequencies closer together, we start to observe a wavering. This is the effect that we call beats. The frequency of the beats is the difference between the two frequencies. These beats occur because the sound from the two speakers alternates between moments of constructive and destructive interference. As the frequencies almost match, our beat frequency slows and almost comes to a stop. As we continue to decrease our frequency, the beats once again speed up. Diffraction. When waves move past a boundary, they bend around it. Larger wavelengths bend more than short. We call this behavior diffraction. So in each of these cases we have a barrier, and we see our longer wavelength bends around more than does our shorter wavelength, meaning that with a longer wavelength we have more diffraction than we have with a shorter wavelength. Plane wavefronts passing through a gap diffract to form radial wavefronts. So if we imagine plane incoming waves passing through a small gap, we're going to see those wavefronts spread out into radial patterns. For this relatively small gap, we're going to observe more diffraction than we would for a larger gap. 2D interference patterns. When two wave sources are adjacent, they produce an interference pattern. The order number n is the wavelength path difference between the sources. Consider our two sources down here emitting our waves. We have our antinodal lines, which are lines of constructive interference. Peaks meet peaks and troughs meet troughs. Amplitudes add to their new amplitude, and our order number is a whole number. Our central antinodal line is n equals 0, n equals 1 on either side of that, n equals 2 on either side of that, and so on. Our nodal lines are lines of destructive interference, where peaks meet troughs, the amplitudes cancel, and our n is something 0.5. Our first nodal lines are 0.5 either side of our 0, and then 1.5, 2.5, and so on. Now to analyze this a bit further, if we were to analyze this point here, we can see we have two wavefronts intersecting, meaning that we have a peak meeting a peak, meaning that we have an antinodal line, which as we can see, we do. If we were to instead consider this point here, we have two wavefronts here and two wavefronts here. Our indicated point is halfway between these two pairs of wavefronts, meaning that it's where a trough is meeting a trough, meaning that we have an antinodal line, which we of course do. If we instead consider this point here, we see that we have a wavefront from one of our sources intersecting with halfway between the wavefronts of our other source, meaning that we have a peak meeting a trough and therefore a nodal line. Path difference. Path difference is the difference in the distance between a selected point and each of the sources. It is usually expressed as a multiple of the wavelength. For example, 2 lambda, 7.2 lambda, or 3.5 lambda. Where the path difference is a whole number of wavelengths, there is an antinodal line. Where the path difference is something 0.5 wavelengths, there is a nodal line. So in our example here, we have 2 sources. For our yellow point, we can count 1, 2, 3, 4, 5, 6, 7 wavefronts. From that, we can subtract 1, 2, 3, 4.5 wavefronts, which gives us a path difference of 3.5 wavelengths. Because our path difference is something 0.5, we have a nodal line. For our green point, we can count 1 wavelength, from which we subtract 1, 2, 3 wavelengths, which gives us a path difference of 2 wavelengths. Because our path difference is a whole number, we have an antinodal line. For our aqua point, we can count 1, 2, 3, 4, 5, 6, 7 wavelengths, from which we can subtract 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 wavelengths, which gives us a path difference of 3 wavelengths. Because our path difference is a whole number, we have an antinodal line. Diffraction formula. Consider the case where we have 2 sources and a position at which their waves are meeting. The distance to the screen is L, the separation of our sources is D, our indicated point is a distance x from the middle, and from our indicated point we have 2 different paths. In this situation, we can recognize 2 triangles. We have this larger triangle and this smaller triangle here. Where these 2 angles are the same, and our opposite side on our small triangle is very usefully our path difference. Using trigonometry on the small triangle, specifically the SO relationship, which is that the sine of the angle is equal to the opposite, which is our path difference, divided by our adjacent, which is our source separation d, rearranging this by multiplying both sides by d to get d sine theta equals our path difference, and then noting that it's often useful to state path difference as a multiple of wavelengths, we arrive at this equation here, which is a very useful equation, but we can also derive another version by making an approximation. For cases where the distance of our screen is much greater than our x distance, we can make the approximation that sine of the angle is roughly equal to tan of the angle. If we now consider the large triangle, using our TOA relationship, which states that tan of the angle is our opposite x divided by our adjacent side L, using our approximation that sine of the angle is roughly tan, we can write the approximation that sine of the angle is x over L. We can therefore substitute for sine of the angle and write this equation here, which is once again very useful, but just be sure to only use it when this is true. Multiple slit interference. Until now, we've only considered 2-slit interference. The case of multiple slits behaves much the same, with several key distinctions. So here's the pattern for a double slit, and here's the pattern for a multiple slit. The pattern for our multiple slit is narrower because more sources are interfering, causing more destructive and less constructive interference. And they are brighter because more sources are contributing to points of constructive interference. Diffraction gratings are a film with thousands of lines, each gap behaving like a slit. They are typically rated in lines per meter. We can relate this to slit spacing using this equation here, that our slit spacing is 1 over our lines per meter. When white light is viewed through a diffraction grating, longer wavelengths appear at a larger angle than smaller wavelengths. So we see our longer red wavelength appearing at a larger angle than our blue wavelength. This occurs because longer wavelengths have a larger path difference, not because they diffract more. This is a common misconception. Now, they do diffract more, but the difference isn't significant, and certainly does not explain this phenomenon. So why is this the case? Consider our longer wavelength and our shorter wavelength. Because we have a larger wavelength, we have a larger path difference, because our path difference is n lambda. Since n lambda equals d sine theta, this means we have a larger d sine theta, and because d is constant, this means our angle must have increased. I have here a diffraction grating
with 100, 300 and 600 lines per millimeter windows, and a column of LEDs of different colors. Viewing these through our grating, we can see that the higher the lines per millimeter, the greater the angles are between our orders. Curved versus flat screen. When antinodal lines are incident on a flat screen, the lines appear to be further apart for each order number. As the angle between the lines is in fact the same, an appropriately curved screen will have equally spaced intersections. So if we imagine our source of our lines, on a flat screen we're going to see the distance smaller in the middle and larger at the edges. However, if we had an appropriately curved screen, we'd see the separation be the same. We also observe the antinodal dots to be brighter towards the middle. This occurs because the light strikes at an angle, causing the light to shift partially out of phase and destructively interfere. So if our light strikes perpendicular to the surface, they all meet in phase. However, if we strike at an angle, our waves are all out of phase. Because they're out of phase, we have destructive interference. Here I have a diffraction grating with 100, 300 and 600 lines per millimeter windows. Turning off the lights and firing up the smoke machine, we can see the interference pattern from this green laser. We can see that the more lines per millimeter, the greater the angle between our antinodal lines. The Doppler effect. Moving wave sources produce wavefronts that are closer to the previous wavefronts ahead and further from the previous wavefronts behind, as seen in this diagram here. And so ahead of our source we have a shorter wavelength, which means a higher frequency, and the velocity of our waves relative to our source is the wave velocity minus the source velocity. Consider that if our source was going at the velocity VW, this would give us VW minus VW and a relative velocity of 0, which makes sense. Our wavelength behind is increased, which means a decreased frequency, and the relative velocity of our wavefronts compared to our source is the wave velocity and the source velocity added together. And if we had an observer perpendicular to the wave velocity of the source, they would observe no relative velocity, and therefore the wavelength and frequency would be unchanged for them. The relative wave source velocity can be written as VW plus or minus Vs, where the plus or minus is a minus ahead, as we saw it was here, and plus behind, as we saw it was here. We can therefore write that our relative wave source velocity is the distance travelled by our wave divided by the time it took to do it. Because our relative wave source velocity is VW plus or minus Vs, we can make that substitution. And the distance travelled by a wave in our period is the literal definition of the wavelength. Because frequency is 1 over period, we can make that substitution. Dividing both sides by frequency and swapping them around, we get this equation. Bearing in mind that we also know our wave velocity is frequency times wavelength, dividing both sides by frequency and swapping them around, we get another equation for wavelength. Because our lambda is equal to this, and our lambda is equal to this must be equal to this. Flipping both sides, which is a thing we can mathematically do, we get this equation here, which we can multiply both sides by VW and swap them around to find that the frequency observed by a stationary observer is the true frequency multiplied by the wave speed divided by our relative wave source velocity, VW plus or minus Vs, where our Vs is the source speed. The key thing to remember about this equation is that our plus or minus is a minus ahead and a plus behind. Doppler graphs. Consider a source approaching us. We would hear a frequency as it moves towards us that would decrease as it passes us to a frequency as it moves away from us. Our true frequency is roughly here, where you might note that the true frequency is not halfway between the towards frequency and the away frequency. The reason is that the observed frequency scales with the proportional difference in speed, not the absolute difference. While the absolute difference is the same, the proportional difference is different. To try and make that make more sense, consider the case where our source velocity is 10 and our wave velocity is 20. Considering the absolute difference between our wave velocity and our wave source velocity, for the towards
scenario, that's our wave velocity minus our wave velocity minus our source velocity, which is 20 minus 20 minus 10, which gives us 10. For our away situation, it is the same, but we have a plus, and so 20 minus 20 plus 10 gives us negative 10, but the absolute difference, meaning the positive difference, gives us the same 10. This is why your intuition might expect the situation to be symmetrical and the true frequency to be in the middle. The reason this isn't true, as mentioned above, is that the observed frequency is scaled proportional to the wave velocity. And so our wave velocity minus our source velocity divided by our wave velocity is 20 minus 10 divided by 20, which gives us 0.5. For away, it is the same but with a plus, which gives us 20 plus 10 divided by 20, giving us 1.5. Now, if you weren't able to 100% follow that, if you're doing scholarship, you may want to spend some time on this, but if you're just doing level 3, it's enough to remember that the true frequency is not halfway.